Have you ever found yourself staring at the back of a tanker truck on the highway and wondering why it's round instead of square, like a standard cargo trailer? That curved, cylindrical design isn't just for looks or some industrial trend. It's actually hiding fascinating science that could mean the difference between absolute safety and a catastrophic disaster that could claim hundreds of lives. In this video, we're going to reveal why these massive vessels of flammable liquid aren't shaped like the rectangular freight trucks you see everywhere else. The answer involves fundamental physics developed over decades, complex fluid dynamics, and surprisingly practical engineering that affects everything. From how the truck handles tight corners to what happens during a high-speed crash. But before we dive into these hidden engineering secrets, as if you love understanding how the things you see every day actually work, hit the like button and subscribe to the channel for more content that reveals the hidden science behind the mundane. Now, let's jump into this fascinating journey. The physics behind cylindrical tanks is where science meets heavy-duty trucking. Have you ever noticed how coffee sloshes violently during a bumpy car ride? That's inertia, working on a small scale. Now, let's imagine that on a massive scale, enough to flip a 30-ton truck. The cylindrical shape of these massive tankers roaming the highways is meticulously engineered with precision. It's based on fundamental principles of fluid dynamics developed through decades of research. When a tanker carrying thousands of gallons of highly volatile fuel has to slam on the brakes in an emergency, or swerve to avoid a sudden obstacle like a stalled car, that the liquid cargo keeps moving forward due to Newtonian inertia. This creates powerful waves that slam against the container walls with tremendous force. This liquid momentum generates measurable, massive force, enough to completely roll a large vehicle if it isn't managed with the right design. In old rectangular tanks, this sloshing creates extremely dangerous, unbalanced dynamic loads. When a liquid hits a flat wall at high speed, it creates an instantaneous, but powerful pressure spike and then bounces back. This often creates a standing wave that oscillates back and forth uncontrollably. It's like watching stadium fans do the wave, but with potentially deadly consequences for the driver. The liquid's center of mass shifts dramatically from side to side, effectively pushing the massive vehicle in dangerous alternating directions. Fun fact number 1. During World War II, Allied engineers discovered that rectangular fuel tanks on warships caused such severe stability issues that some vessels capsized in rough seas without taking any enemy fire. This military discovery led directly to the post-war development of cylindrical tanks for land transport when veterans returned to work in civilian industries. Why cylinders win is physics in visible action. Let's look at how the cylinder converts liquid chaos into calm by dispersing energy around its smooth, continuous curve. When liquid sloshes violently inside a cylinder, the curved walls simultaneously redirect the kinetic energy in multiple different directions. Instead of creating powerful, destructive one-way waves, the cylinder disperses that energy along its inner 360-degree circumference. This creates smaller, counter-rotating currents that effectively cancel each other out mathematically, neutralizing much of the dangerous movement that could cause a rollover. At a microscopic, molecular level, the difference becomes even more evident and fascinating for physicists. In rigid square containers, liquid molecules crash against flat surfaces and bounce back with most of their kinetic energy intact. Curved cylindrical surfaces, however, create complex boundary layer effects that engineers study closely. Imagine how sound travels evenly around a circular stadium, instead of bouncing off a flat wall and creating an echo. And the curved geometry naturally dissipates kinetic energy through increased turbulence and distributed, controlled friction. In real-world tests conducted by safety engineers, it was observed that old rectangular tanks suffered pressure spikes up to 3 times higher than modern cylinders. Imagine a 30-ton lateral shove trying to push a truck out of its lane and into oncoming traffic. Rectangular tanks experienced side forces strong enough, and to shift a vehicle's center of gravity beyond its critical stability threshold. Meanwhile, cylindrical tanks maintained safe operating parameters under the exact same test conditions. Fun fact number 2. A fully loaded tanker can carry up to 11,500 gallons of liquid fuel, weighing over 38 tons in total. The liquid inside moves with so much force during emergency braking that without the proper cylindrical design, the fuel's inertia could generate forces equivalent to a second full truck, constantly pushing from behind. Strength by design, built to withstand massive extreme pressure. The advantage of pressure distribution extends far beyond just liquid sloshing while driving. The static pressure from the weight of the liquid presses equally in all directions, according to Pascal's law, a fundamental principle of physics. But old rectangular tanks concentrate this continuous stress in the corners and seams where flat surfaces are joined by welding. These joints become natural failure points where metal fatigue occurs gradually over time and through loading cycles. Modern cylindrical designs completely eliminate these structural weak points by distributing pressure evenly across the entire curved surface without dangerous concentrations. And it's similar to how a classic architectural arch can support massive weight by distributing compressive forces. This fundamental geometric principle explains why military submarines use cylindrical pressure hulls to operate at extreme ocean depths. At extreme ocean depths of several miles, massive water pressure would instantly crush a square vessel by concentrating destructive forces on vulnerable flat surfaces. Cylindrical designs, however, distribute these enormous pressures effectively through continuous curved geometry. The cylindrical shape also creates inherently self-damping wave patterns that fascinate physicists. When liquid moves in a circular container, every wave naturally generates counterwaves that propagate around the full circumference. These waves interfere with each other in a complex pattern resembling ripples in a calm pond. But they tend to cancel each other out rather than destructively amplifying each other's energy. It's an elegant self-regulating system designed by the immutable laws of physics. Fun fact number 3. Engineers use a principle called resonance frequency to design tanks optimally. Every tank has a specific natural frequency at which the liquid oscillates most violently and dangerously. By mathematically calculating this critical frequency and designing strategically placed internal baffles, they can disrupt these dangerous oscillations before they generate the destabilizing forces that could flip the entire vehicle in a sharp turn. Structural integrity and rigorous safety standards are often written in blood. Safety is the absolute #1 priority, without exception, while preventing liquid movement makes tankers safer during routine daily driving. What happens when disaster strikes in the form of a collision? In the split-second chaos of a high-speed highway crash, the difference between cylindrical and rectangular tanks isn't just about stability. It's measured in lives saved and communities protected from massive catastrophes. Every single workday, thousands of tanker trucks navigate through dense city traffic, carrying what are essentially giant mobile bombs. Up to 11,500 gallons of highly flammable liquid that could level entire neighborhoods. When these vehicles collide violently, the structural integrity of the tank becomes the only thin barrier. Yet between a manageable accident with minor damage and a catastrophic explosion that kills dozens, this is where the cylindrical design proves its worth beyond just preventing sloshing. The impact forces of a collision behave similarly to extreme hydraulic pressure, searching for the path of least resistance through the material. In old rectangular tanks, these destructive forces concentrate dangerously at the corners and seams where flat surfaces meet. And this is where catastrophic structural failure is most likely to occur. Think of it like cracking a chicken egg. It breaks first at its sharpest, weakest points. A modern cylindrical tank, however, intelligently redirects impact energy around its curved surface. It dissipates the destructive force instead of allowing it to concentrate on a single vulnerable area. This principle of force distribution was tragically demonstrated in the historic Kingman, Arizona disaster in 1973. And a propane tanker with rectangular sections was involved in a routine railroad crossing accident. This led to a massive catastrophic explosion that killed 11 brave firefighters and seriously injured nearly 100 innocent people. The rupture began exactly as engineers had theoretically predicted, at a weak seam where two flat surfaces met at an angle. The weld failed under the stress concentration. This and several similarly tragic accidents throughout the 1970s catalyzed a comprehensive, industry-wide regulatory reform. In response to public pressure, the U.S. Department of Transportation developed the first modern safety standards for transporting hazardous materials. The 49 CFR regulation specifically mandates cylindrical designs for most flammable liquids with detailed technical requirements. These include specific wall thickness, certified material composition, and exhaustive pressure testing before approval. European regulations followed suit with strict ADR standards. The European Agreement concerning the international carriage of dangerous goods by road created a global consensus on safe tanker design. These aren't just annoying bureaucratic paperwork. They are engineering requirements, literally written with the blood of past victims who died unnecessarily. Compliance testing is brutal, relentless, and designed to fail weak designs. Tanks must withstand being dropped from heights of 9 meters. They are exposed to 1,000-degree open flames for prescribed periods and subjected to puncture attempts from standardized equipment simulating accidents. Only designs that can maintain their structural integrity under these extreme conditions receive official certification to operate. Scientific data supports these strict regulations with hard statistics. Studies comparing pre-regulation tankers with modern cylindrical designs show a dramatic reduction in post-accident fire and explosion rates of approximately 25%. This translates to hundreds of civilian lives saved since these standards were implemented in the 1980s. When accidents inevitably happen today, cylindrical tanks are significantly more likely to remain structurally intact or sustain minor, manageable breaches rather than total catastrophic failure and massive explosion. Fun fact number 4. Modern tanker trucks must pass a drop test, where the entire tank is dropped from a height of 9 meters onto a reinforced concrete surface. The cylindrical tank must remain completely sealed without any leaks. Old rectangular designs consistently failed this test at the corners, where welds snapped from the concentration of impact forces. And this brutal test has saved countless lives by ensuring only the most robust designs hit the roads where they carry millions of gallons daily. Cleaner, cheaper, safer, cylinders simply do everything better. An often overlooked benefit of the cylindrical design emerges during routine maintenance and regular cleaning. Old rectangular trucks develop inaccessible, hidden corners where residual materials can dangerously accumulate over time. And this creates cleaning challenges and potential hazardous chemical reactions between incompatible residues. Modern cylindrical tanks allow for much more effective cleaning procedures, using automated systems that can reach every internal surface without leaving blind spots where contamination can build up. This dramatically reduces the risk of cross-contamination between different loads, and it significantly extends the operational life of expensive equipment over decades. So there is a substantial economic dimension to these safety features that companies appreciate as well. The aerodynamic efficiency of the cylindrical tank creates measurable fuel savings of 5 to 7% compared to angular, box-shaped alternatives. For a tanker traveling 100,000 miles across the country annually, that represents approximately $20,000 to $30,000 in fuel cost savings per vehicle every fiscal year. But with fleets often numbering in the hundreds of heavy vehicles, large transport companies save literally millions of dollars annually, while simultaneously operating much safer vehicles that reduce liability. Insurance costs also reflect these safety improvements significantly in their premiums. Premiums for hazardous material transport have actually decreased relative to general inflation since the implementation of mandatory cylindrical tank regulations. And despite the increasing value of modern vehicles and the rising cost of the cargo being insured, insurance actuaries have coldly calculated with numbers what engineers have known for decades through experience. Cylindrical tanks save substantial corporate money and valuable human lives at the same time. Regulatory standards continue to evolve with emerging new technology. Modern, state-of-the-art tankers incorporate additional advanced safety features like strategically located internal reinforced baffles, specialized automatic pressure relief valves, and advanced composite materials are now built upon the proven, fundamental cylindrical design. Some technologically cutting-edge tankers even utilize double hull construction for extremely hazardous materials, creating a redundant safety system inspired by modern maritime oil tankers. Fun fact number 5. The internal baffles inside cylindrical tanks aren't solid walls that block flow. They have calculated, strategic openings that allow fuel to flow slowly, but they prevent large, dangerous waves from forming. It's like having internal breakwaters that calm the liquid ocean inside the tank, without completely blocking the flow necessary for efficient loading and unloading operations. So, what have we learned about these shiny giants of the road? The characteristic roundness of fuel tankers isn't just casual, clever engineering or a designer's whim. It's a remarkable example of how form perfectly follows function in optimal engineering. These shiny cylindrical wonders represent the perfect intersection where fundamental Newtonian physics, government safety regulations, and corporate economic efficiency all point toward the same optimal design solution. The next time you're driving your car alongside one of these giant, silver tubes on the highway, you'll have a deep appreciation for the invisible forces constantly at work, all to keep that dangerous, volatile cargo completely safe for everyone. It's an impressive testament to collective human ingenuity that something seemingly so simple required decades of expensive scientific research. Tragic lessons were learned through lost lives, and continuous scientific innovation was used to perfect every last detail. Every perfect curve, every reinforced weld, every strategic internal baffle. It all represents years of meticulous development and exhaustive testing performed by teams of engineers. What other mundane, everyday objects around you hide similar fascinating stories of brilliant design? Let us know in the comments and subscribe to the channel for more eye-opening videos like this that reveal the hidden engineering behind the ordinary. Give us a like if you learned something new today about these cylindrical giants of the road that carry the fuel that moves the world. We'll see you in the next video, where we'll uncover more secrets.